Hey folks, this video 2.2e, we start jumping into Newton's second law practice problems. So if you're following along in that packet that I gave at the beginning of this unit, you can take that out to take notes. Otherwise, you can write everything along with me. So we're going to do 3 problems in this video. The first problem is a free body diagram that's been done for you, and then it says calculate the acceleration of this 2 kilogram object. So the free body diagram has forces in 2 dimensions. And so basically what that means is you are going to need to write out 2 Newton's second law equations. Now, later on, you're probably not going to need to do all of this work because you can look at a free body diagram and make this inference, but for now, we're going to do it all. By the way, this is about as good as it gets for me writing sigmas while doing problems on paper. So the net force in the x direction, the net force in the y direction. I'm going to start with the net force in the y direction. I have 2 forces, and I'm going to make up the positive direction, 20 newtons and 20 newtons. So I'm going to add those forces, the 20 newtons up plus the 20 newtons down equals mass times the acceleration in the vertical direction. And so what that all means is that the vertical acceleration is 0. So in the future, you can either ignore it if the problem allows for it, or you can just skip right to the idea that the net force is going to be 0 because the up and down forces balance. Just be careful with that for now. All right, the x direction net force. Now, in general, I'm going to make right the positive direction, and so I'm going to add my forces in the following way. The positive force in the x direction is 15 newtons. I'm going to add to that the 25 Newton force, which is in the negative direction. That's equal to mass times acceleration. Now I'm actually going to put 2 kilograms in there and my variable of acceleration in the x direction. So I'll show all my workout for now, and then I'll skip this in the future. The net force is going to be negative 10 newtons. And that's equal to 2 kilograms times the acceleration. And I'm going to divide by 2. And so I get negative 5 meters per second squared is the acceleration. Now, if you're asked to turn this into like words, then you would say that the acceleration is 5 meters per second squared to the left. If you're given cardinal directions, you can use those or otherwise, but that's it. Okay, moving on. Next one. A 2.5 kilogram object accelerates at 0.75 meters per second squared to the right due to an applied force of 3 newtons. What is the magnitude of the friction force? So this one doesn't have a free body diagram, so we're going to make one. Applied force is 3 newtons. There's a friction force. Now this friction force needs to be in the opposite direction. If the applied force is pushing it one way, friction will push the opposite way because it's going to be sliding. There's also a gravitational force, and because there's friction, there has to also be a normal force because it's got to be on a surface. Now we know the acceleration is to the right. Now something about the language here. When it says the acceleration is to the right, that actually means that the acceleration is in no other direction but right. And you can take that to any vector in this course. If it says that it points to the right, it cannot be pointing in any other direction, so we can now ignore the vertical component of net force. So I will go straight to the net force in the x direction equals mass times acceleration. I'm going to solve this in one equation. You might feel more comfortable solving this in 2 steps, but I'm going to show you how to do it in one because I think it's the better way to do things. I'm going to add my forces. Now, I'm going to make the right the positive direction unless I have a good reason not to. And so my net force is 3 newtons plus the friction force, which is in the negative direction. The mass is 2.5 kilograms, and the acceleration is in 0.75 meters per second squared. And so that is my equation for net force equaling mass times acceleration. I'm not going to show my work for this one. And I'm just going to like show the answer. And if you have a question about how I got that answer, you can do that. Now it says magnitude, so I don't need to assign a direction to this. If you did assign a direction, it would be to the left or negative. But that negative sign right there in my work actually shows that the friction force points in the negative direction. So 1.1 newtons is all we got. This last one is more just to teach a lesson about free fall, and one that you never need to repeat. A 0.25 kilogram ball is dropped from a height of 8.6 meters. Calculate the time it takes to reach the ground. So doing things very formally, when a ball is dropped, there is a force of gravity, and we assume that there's no air resistance. And so that is a complete free body diagram for that object. Now I'm going to make up the positive direction. You can also do this by making down the positive direction. There is a net force in the y direction. And that net force is due to the force of gravity. So maybe you remember from your notes that the force of gravity is equal to the mass of an object times little g. So my net force in the y direction is going to be negative Fg, because it's pointed down, and I decided that up was the positive direction. Now I'm going to make a substitution. Fg is equal to mg, and so negative mg equals mass times acceleration. Mass appears in every term in this equation, so I can divide both sides by m, and it will cancel mass, and I arrive at negative g is the acceleration in the y direction, which is what we already knew from kinematics. So this is just proving that objects in free fall have a constant acceleration of negative g. All right, well now I can answer my question. Calculate the time it takes to reach the ground. I have the height, and I have the acceleration. I have it dropped, so I have the initial velocity. So I'm going to use this equation. All right. Now the initial velocity is 0 because it was dropped. The final position of this ball is 0 meters. The initial position is 8.6 meters. The acceleration is negative 9.8 meters per second squared. And so t squared is my variable. So again, I'm not going to show my work. You can ask me questions if you need to. And so the time to fall is 1.3 seconds. And that's that. So start doing some problems, and then the next video will get you into a more complicated situation.